This conference will now be recorded.
Yes, we can see.
Thank you. Right. Okay. So thank you for joining, everyone, and thank you for inviting me. I'm going to give a talk this evening titled Investigations into the Weather-Driven Deterioration of Railway Earthworks. And this is an update from the EPSRC-funded Achilles Programme, which is formed from a number of universities and the British Geological Survey, and you can see them along the bottom of the slide. So what I'm going to do today is talk about the programme, some different aspects of the programme, and then I'll go into more detail by presenting some results from a recent paper that was published by the group. And I've chosen that paper to present because it actually incorporates information from the different universities across the whole programme. So just to introduce myself, I'm an HS2 and Royal Academy of Engineering Senior Research Fellow at the University of Bath. That fellowship runs from 2020 to 2025, and I'm the PI for the Achilles project in terms of from the University of Bath, which is also a project that's currently underway. Previous railway experience is I had a Royal Academy Industry Fellowship with Network Rail about 4 years ago, working with the Infrastructure Design Group. My engineering doctorate with Southampton University was sponsored by Mott MacDonald, and during that time I undertook some applied research for Network Rail and London Underground, looking at climate impact on earthworks and looking at vegetation impact on earthworks. But actually my first industrial experience when I was an undergraduate student was actually in Permanent Way, and that was in the Permanent Way team at Owen Williams, based in Swindon, on the Great Western and also the Crude Holyhead line. But today I'm here presenting on behalf of Achilles. So the Achilles team is, as I say, an EPSRC project, and it has 6 universities and the British Geological Survey. So you can see the universities there on the right and the different academics in those groups. And we have a number of industrial stakeholders as well. So the project program started in 2018 to 2022, and Achilles stands for the Assessment, Costing and Enhancement of Long Life, Long Linear Assets. So we're looking at the weather-driven deterioration of earthworks, and particularly those for road and railway transport, so embankments and cuttings, and also small amount of work looking at pipeline bedding and flood protection structures, which is a new part of the project relative to earlier projects. And you can see a photo of the group there taken in Bristol probably about 3 years ago now. And the project's led by Professor Stephanie Glendinning, who's professor at Newcastle University. But amongst the team, we have geotechnical engineers working at different scales. So we have people working in the lab, we have people who do numerical simulations, we have people who do field monitoring, imaging with X-ray CT, and critically to this project, we have statisticians as well, which is really helping us to look at, which I'll present in a moment, but it's helping us to look at root scale deterioration of earthworks. So this is the go-to slide for the program, and it's a performance curve. So what we see here is performance on the y-axis from high to low, and along the x-axis we have time. And time is looking at the age of earthworks assets. And we refer to this as the upturned bathtub model, which is the black line, which on the left goes up, then it flattens out, and then it drops off again. And we're using this to conceptually describe the performance of an asset over its lifespan. So initially an asset will, by asset I mean an earthwork, will be bedding in. Then during the main part of its life, it will have reliable performance, which is along the top. Then it will start to degenerate and become unreliable. And at some point that black line drops below some performance threshold. So performance could be a number of measures depending on what scale we're looking at. But for example, it could be factor of safety versus time, or slope deformation versus time, or maintenance cost versus time. And this relates to our asset owners. So I mentioned at the beginning, we have a number of stakeholders supporting the project and really supportive of the project. And we can see where they might map against those different ages. So new assets might be the HS2 earthworks, which once they're ready, they would then be bedding in for a number of years. Then Highways England, or National Highways now, have a number of assets that of sort of intermediate age. So at the moment, they might be in a reliable stage of their life, but they might be moving towards some stage when they start to degenerate. And then we have Network Rail, which has some of the oldest assets, going back to Victorian period, and these will be in a state somewhere between reliable and degenerating, and some might be unreliable if they're being repaired. So that's the conceptual model of performance that we have underpinning the project, and this helped us to set up 3 research challenges, which are RC1, 2, and 3. So research challenge 1 is looking at deterioration processes. So there are groups within the program looking at how materials deteriorate, particularly clay materials, because we're looking at weather-driven deterioration of high and medium plasticity clay slopes. Research challenge 2 is looking at asset performance. So that can range from, starts by looking at material behavior, but then looks at the performance of earthworks and cuttings and slopes. So that could be stability analyses, and actually the paper I'll present will focus on this second research challenge. We have a final research challenge, which is about forecasting and decision support. And what we're doing here is taking that understanding of slope scale earthwork behavior and looking at what that might look like across a route of assets or a network of assets. And that can include things like looking at the stability of the and reliability of the earthworks, but also looking at implications in terms of design and decisions that you can make around design, decisions around maintenance, and also the financial aspects of that. So we have a team, we have 2 economists in the project as well who are linking the earthwork behavior to cost implications. So I'm just going to talk through some of the key areas of Achilles before going into the main presentation. So the first concept in the project is performance, and we're describing this as a change in the safety or serviceability of a single asset or a route or a network of assets relative to some threshold, which is an expectation. So for example, on here, we're plotting, this is showing what that might look like in terms of a safety or a service performance over time, and how actions that we can take, such as maintenance, repair, or refurbishment of an asset, can actually improve that performance once it starts to deteriorate, or we might replace that asset and bring it back up to its full performance again. The second core concept is the concept of deterioration. And this is where we say deterioration can be used to describe a change leading to a loss of performance with respect to an expectation. So within this project, what this means is we're looking at weather-induced change, and we're looking at changes in strength, stiffness, structure, or the hydraulic properties of a soil element, like something you might test in the lab, or of an asset, so thinking about the slope scale. And this is where our conceptual model is currently at, has 4 quadrants. Those on the left relate to deterioration of structure in the material or in the slope. So that refers to things like wetting and drying cycles causing the cracking and breakdown of soil, and any irrecoverable deformations. And on the right-hand side at the top, we have deterioration of soil hydraulic properties. So changes in permeability, for example, or changes in the soil water retention properties of material. And then the bottom right, we have changes in soil strength and stiffness, so strength reduction or stiffness reduction. This conceptual model is populated, there's a lot of literature supporting these different quadrants and these different statements, and these underpin the investigations that we're undertaking within the program. And as the program progresses, we're adding to this conceptual model, so we're improving our understanding. And we have a number of projects or small investigations that actually cross those different quadrants as well. Particular strength of the project is we have access within the Achilles program. We have these long-term field monitoring sites. So they are earthworks that have been instrumented some time ago and continuously monitored since. So to show you two of these, the first is the Newbury-Highbury cutting, which is a London clay cutting that was constructed in 2003 and has been monitored since then by Southampton University. And it includes instruments including weather station, piezometers, they measure moisture content, and in situ experiments are undertaken there at different seasons, etc. Another of our key sites is the test embankment in intermediate plasticity clay, which is called Bionics, and this is up in the northeast. And this is a purpose-built test embankment, again, fully instrumented. I think it was constructed in the early 2000s, and there's also facilities there to simulate weather conditions. So there's a frame you can just see in the picture there where you can create rainfall events, etc. So these are really important to the program because they provide long-term data of how the weather is influencing the earthworks, and by the nature of being over many years, we're able to capture winters and summers of different degrees, so particularly wet winters or particularly dry summers, or any other combination that's happened in those 16 or more years. Another aspect of Achilles is the laboratory testing. So the images here are from Durham University. And what we can see here is investigations, for example, in the top left-hand corner, looking at the influence of wetting and drying cycles on cracks forming in very small samples and looking at how those cracks propagate and then influence the material properties in the lab testing. So this is linked to other lab tests, such as those looking at the soil water retention properties of high and medium plasticity clays and how these change or degrade over time due to wetting and drying cycles. And in the bottom right hand corner, you can see how this has been linked to changes in strength due to the wetting and drying cycles as well. So again, addressing these concepts of structure, hydraulic properties, and strength deterioration. We have a number of slope scale simulations, and that's what the main presentation is going to be about today. So shown here is some work at Newcastle and Loughborough University, where there's a model, finite difference model has been created in FLAC. It's a coupled hydromechanical model where we can simulate the weather conditions on the slope surface to simulate the pore water pressures, and then finally the mechanical response of that slope. And some typical results you can see there in the bottom right. So here, for example, versus time, we have pore water pressure in the simulations at different points within the slope so you can see they're at different depths for medium climate, and also a medium climate with extremes put into the model. And an output of the model is we can then compare, for example, changes in factor of safety over time. And we call these deterioration curves. So we can see the reduction in the factor of safety over time due to the weather cycles on that slope. As well as looking at the slope scale, I mentioned we have statisticians on the project. So this enables us to take our learning use those simulations, which are quite time intensive to run, these deterministic finite difference models, to explore what this might look like at the root scale or the slope scale. So here's an example of the statistical emulator. So on the left-hand image, you can see different slope angles and slope heights, and these were used to create 76 slope scale simulations. So these were run in the numerical model with the weather data, etc. And here they were varying the geometry of the slope. And you can see those boxes are colored, and that's because they've been matched to real assets on the Network Rail and National Highways databases. So these represent different road and rail cut slopes. Using the statistical emulator and clever selection of which models to run, you can then emulate 900 models very quickly. So this incorporates slope scale parameters such as the material and the geometry and boundary conditions to simulate the behavior of a whole network of assets. And some typical outputs is along the bottom there, you can see the variables that are in the emulator and the ranges of those different variables. So slope height, slope angle, the drained material properties, and the permeability. And a typical output of the emulator looks something like the figure on the right. And so here we can see for different slope heights and slope angles, the forecast lifespan of those earthworks. And unsurprisingly, the very tall, very steep slopes have the shortest lifespan, and the shallower, shorter slopes have a much longer lifespan. And this has been compared to failures in earthworks nationally. Okay, so this brings me to today's talk. So what I'm going to present is the results from a paper that was published in 2021, so earlier this year. And the title of that is Forecasting the Long-Term Deterioration of a Cut Slope in a High Plasticity Clay Using a Numerical Model. And the numerical model you can see there in the center of the slide. So it's a coupled hydromechanical model that was developed at Loughborough and Newcastle University. And I'll give more details in a moment, but the reason I've selected this is it brings together inputs from many of the other partners across the program. So for example, it's a model of the Newbury site. So we have the monitoring data from that, you can see in the top left. And we have in situ measurements from that site and from other Achilles earthworks to help us get the right parameters for the permeability, for example, which is shown on that figure. And in the top right, Southampton and Newcastle University developed a slope-specific synthetic weather generator. So I'll talk about that a bit more in a moment, but it allows us to extrapolate beyond the 16 or 20 years of monitoring and consider what a 120-year design life, behavior over 120 years might be, because that relates to the design life of many earthworks. One important feature of this model, which you can see in the bottom left-hand figure, is that this is a numerical modeling issue really, but there's some recent work published last year, 2020, from Loughborough and Newcastle Universities, which uses a new approach to model strain softening in clay materials, which I'll describe in a moment. And that is a key feature of this model as well, and it is key to one of the conclusions. So what were we using this for? Well, we were simulating seasonal pore water pressures, investigating a slope ratcheting mechanism which develops over time, looking at strain softening of the slope and how these contribute to the deterioration of soil strength and how that contributes to changes in the dominant failure mode of the cutting over time. So we're forecasting what that might look like over the full 120 years. So the aim was to simulate the long-term deterioration of a cut slope. And this was in response to two things. The first thing was the dissipation of post-construction pore water pressures, which is a known behavior, and also to look at the slope ratcheting induced by repeated seasonal pore water pressure cycles, which is a new behavior in the model, at least. So the objectives were to build a coupled hydromechanical model of the Achilles Newbury slope using inputs data from that site, so material properties, slope geometry, and the weather data. And the second objective was to validate the model against the monitoring data from that site for those 16 years. The third objective related to forecasting, and this was to build a synthetic weather data series to simulate future weather data. And this focused on the concept of soil moisture deficit, because as I'll show you in a moment, not all weather events are the same. And finally, the fourth objective was to simulate what this might look like over 120 years, which relates to the design life of an earthwork. So this was to look at the dominant failure mechanisms and what role different deterioration mechanisms have over time. So I'm just going to go through the methods and the results now. So the Newbury site is a highway cutting, which was constructed in 1997, and it's in London clay with some weathered London clay at the top, and it's been instrumented since 2003. So the instruments are piezometers, neutron probe, weather station, and as I mentioned before, there are in situ experiments that have been undertaken there. It's a grass-covered slope, and on the top left-hand figure, you can see that there are groups of instruments, group A, B, C, and D, going from the top crest to the toe of the slope. You can see where Newbury is relative to London and Cardiff, and in the bottom right, you can see some results from some tests that were undertaken at the site. So these particular ones I've shown are showing how the we could say permeability, but the saturated hydraulic conductivity varies with depth, and you can see it varies by orders of magnitude over a very short range at the near surface. And actually, this was quite critical to the way that the model ran. So in terms of the geometry and the materials, we used the finite difference software FLAC two-phase flow. So the modelers were able to simulate saturated flow in the slope and also unsaturated flow. The geometry was based on Newbury, as were the material properties, which were drawn from in situ and laboratory test data. And these included, for example, soil water retention properties, SWRCs. Importantly, the London clay was simulated as a strain softening material. So that's shown in the figure just below. You can see plastic strain versus shear strength. So it's saying that as the material strains, in this case due to shrink swell cycles, there's a reduction in strength. So you could, in the model, they characterize the peak strength, the post-peak strength, and the residual strength, which is at the larger strains. So the model was run to simulate changes in port pressure, material strength, and then any changes, any deformations, so changes in geometry. So this model included a recent advance in material simulation. This came from Postil et al. 2020, and this was a model. This is a technique in the modeling for non-localization of plastic strains. And this is important because this was the first to simulate the ratcheting mechanism measured by Take and Bolton in 2011. So Take and Bolton in 2011 published a paper which was based on centrifuge testing, where a slope was put in the centrifuge and subjected to wetting and drying cycles. And what they showed is the response of that slope to those wetting and drying cycles was to ratchet, to move downwards and outwards with each cycle. And when this was simulated by Postil et al., they were able to replicate this behavior. And that's what's shown on the right. So we have horizontal and vertical displacement of the model, the physical model from the centrifuge, which are the circles, the dots, and the dashed line is the numerical modeling results. And as you move from D to E to F to G and H, the physical model and the numerical model are going through wetting and drying cycles. And as that was happening, what was happening this is the crest of the slope, is, as I say, this ratcheting mechanism of downwards and outwards movements. So by incorporating this, they were able to replicate that ratcheting mechanism that was seen in the physical model, the centrifuge model, and also has been observed in the field as well. So the boundary of condition, there were three boundary conditions to the model, which feature at different times. So the first condition was to simulate the excavation process of the cutting over 72 days, and this was really simulating the release of the in situ stresses when you create a cut in the ground. The second condition was to apply a boundary condition to the model based on the Newbury weather station data. So they used 16 years of data to derive a surface water balance from the rainfall, evapotranspiration, recharge, and runoff. Then the third condition was to look towards the future, or forecast what might happen in the future using this synthetic weather data. And this was based on a soil moisture deficit, which I'll describe in more detail. So the boundary condition one was quite self-explanatory. That's the release of the stresses due to the cutting. Condition two is the weather station data. So in the top right-hand corner, there's a diagram showing what that boundary condition looks like. So you have water moving into the slope due to rainfall, water being removed from the slope due to evapotranspiration, and some water running off the slope. And the way this can be described is with a soil moisture deficit. So soil moisture deficit is the amount of water in millimeters, so it's one-dimensional, that you would have to add to the soil to recharge it to saturation. So it's a balance of those different inputs and outputs. And what it says is when the soil is fully saturated, SMD is 0, and when it's dry, it's some number above 0. Critically, what happens is when it's saturated, so when it's 0, even if it rains, that rainfall doesn't go into the slope, it runs off the slope. We can see this in the image on the left. So this is actually taken from Smethurst et al. 2006. So this is not a simulation. This is measured data and a very simple SMD model. And what we see versus time on the x-axis is at the top we have the daily rainfall, which you can see is distributed throughout the year. And on the bottom we have the soil moisture deficit. What you'll see is in the winter months, when evapotranspiration is low and rainfall is higher, SMD is close to zero until it gets to zero, and then any other rainfall will run off. Whereas in the summer months, for example, you can see through August and September there, gradually over time, there's become a deficit of moisture in the soil where evapotranspiration is greater than rainfall over a long period of time, and this builds up cumulatively. So by the end of September, October, the soil is at its driest, and as we move into the winter, evapotranspiration reduces because temperatures reduce, the length of the days reduce, etc. And that rainfall becomes more effective and it infiltrates into the slope, and SMD moves back towards zero. So this is important for our climate in the UK because we have this seasonal climate. So whether it rains in the summer or the winter actually has a different impact on the hydrology of the slope. And it's these long-term effects. And because the clays have quite a low permeability, it's actually these longer-term cumulative changes in the water balance or the moisture deficit that actually affect the hydrology of the slope. Okay, so the third condition was this future synthetic data, and this was derived by first converting the weather data into soil moisture deficit and then creating this stochastic synthetic weather data. And this was generated from long-term regional weather data between 1961 and 1990. So this will be more representative because it's over a 30-year period than repeating the Newbury data, which is only 16 years long, multiple times. And as I say, this was based around SMD because it's critical to the way the slopes respond to our seasonal climate. And we're able to compare this synthetic data to the more limited, but still quite long, 16 years of data from Newbury. And this is how we generated this 120-year weather sequence. So you can see some comparisons there on the left. So they're all versus time. And so at the top, you can see PET, which is potential evapotranspiration, cumulative, cumulative for each year. And you can see in grey the synthetic data, and in black you can see the Newbury monitored data projected onto that. Next we can see the rainfall, same thing, so the synthetic data is in grey and the Newbury data is in black. And we can see how this manifests as a soil moisture deficit in the bottom figure. So remember that SMD 0 is when the soil is wet, and when it's some number above 0, that's when it's dry. And this shows both the synthetic data and the Newbury data. And what's interesting about this is if you look at the summer of 2003, particularly, and the 2005, you can see that the Newbury data over those 16 years actually captures two very dry years. Similarly, you can see in the winter of 2008 to 9, SMD is very low relative to the other years. So within the Newbury weather data set, there's also a very wet period as well. A wet winter, we call it. Okay, so I've explained some of the inputs to the model. Now I'm going to explain some of the results. So to the right, we have a figure of pore to pressure versus time from two locations in the model, the simulation, at 1.5 meters and 1 meter depth, respectively. And what these show is that within the model, they're able to replicate these seasonal cycles of pore to pressure, which are shown in blue, and compare these to the piezometer data from Newbury itself. And you can see it's not an exact match, but over that long period of time, you can see that it's capturing some of those dry summer events and some of those wet winter events. On the left-hand side, we can see what this, how this looks over the much longer time period. So here, shown over 90 years, is the pore to pressures at 3 different depths versus time, going from shallow in the top figure to the deepest position location in the bottom figure. What we see here, so this is with all the conditions applied. So the post-excavation release of stresses, then the 16 years of Newbury data, plus the forecasting boundary condition data. What we see here is the initial recovery of the suppressed pore water pressures due to excavation, and this progresses with depth. And then beyond that, we see an annually stable but seasonally cycled pore water pressures, and these are greatest at the near surface. So the grey lines show the pore water pressure calculated every day, plotted there, and you can, unsurprisingly, you can see those seasonal cycles, which are quite large at shallow depth, at 2.5 meters depth, whereas when you get down to 10 meters depth, they're more suppressed. Again, and with the black line, which is the moving average, here we can see that recovery of the long-term pore water pressures due to the excavation. This is most obvious in the bottom figure, so you can see that it's increasing over about 50 years before then stabilizing. So initially the pore water pressures are dominated by this release of stresses, or their stress response, and then in the longer term, they're being influenced by those seasonal weather cycles. In this figure, I'm showing the mechanical response. So here I'm showing data from the 16 years. So in the top, we see the pore water pressure versus time, and you can see that it's varying seasonally. And shaded grey, you can see these prolonged wet periods where actually the pore water pressures were a bit higher or closer to zero than they were in other winters or other years. And in the two figures below, we can see the movement of the slope, or the simulated movement of the slope over time. So x-axis is horizontal displacement and the y-axis is the vertical displacement. And then that line traces wetting and drying cycles, and there are red dots to show each yearly interval. So what we can see in these, if you look at the central figure, is the seasonal ratcheting mechanism. So we can see it at the mid-slope and then later at the toe, which is the bottom figure. So by ratcheting, each year the slope is moving outwards and downwards, outwards and downwards. And at the toe this is happening as well, but it's a bit delayed because initially it's dominated by the swelling of the excavation. The second thing to notice is that the largest outward movements are during those wet winter periods. So during a particularly wet winter or wet couple of years, that's when you might expect the greatest horizontal displacement in the slope, or the greatest amount of ratcheting. What we can see here is the longer term response. So this is when we used 120 years of weather data. So the black is the past weather and the grey is the synthetic weather. I should mention there's no climate change in these particular simulations. We have been looking at that, but this particular study is looking at what would happen if our current weather just continued as it was for 120 years. What we see, again, if you look at the bottom figure, is we see this outwards and downwards ratcheting movement of the mid-slope to around 15 to 20 years after excavation. And again, there's this greater outward movement during the wet weather periods. So what are the implications for slope stability? Well, we wanted to consider this in terms of factor of safety. So after each simulated year, we used a limit equilibrium model to calculate the factor of safety. So it took the pore water pressures and the shear strength, particularly the strain softened shear strength that it had got to by that point, and this was put into a limit equilibrium model each year. And one particular comparison was to look at this influence of strain softening on the long-term deterioration of the slope, and that's what's actually shown in the figure here. So the grey line is what you've seen in previous models, that is how the factor of safety would change if that simulation was run and there was no strain softening. So it was just due to effective stress. The strength changes were just due to changes in effective stress. The black line has the softening model. So this is saying that the strength changes due to effective stress, but it also deteriorates. So it also reduces because it's softening as it's straining. And what we can see here is that both models are very similar initially, and they show an initial reduction in factor of safety due to excavation and swelling in response to the excavation. But over time, the strain softening, so after about 10 to 15 years, the strain softening begins to influence the slope stability as well. And that's why the black dashed line, lies below that grey line. So the factor of safety in the strain softened slope is lower than that in the model with no softening. So this is showing the same information again in the top left-hand corner, and in the top right-hand corner, it's also showing how the slope failure mechanism also changed within the simulations over time. So we can see that in the top left, the deterioration of the slope is ranked here, scaled 0 to 1 on the y-axis, and we're showing that the grey shaded area is showing the initial slope stability deteriorates due to these post-excavation pore water pressures, and in the simulations this led to a deep-seated failure mechanism. We can also see with the blue shaded area that over longer time periods it also deteriorates due to cyclic pore water pressure, and these drive ratcheting and material softening. So as we get to those longer time periods, say 80 or 90 years, the blue shaded area is actually quite a large contribution. It contributes quite a large part towards the deterioration of the slope. And this most softened zone is generally at shallow depth, and therefore it drives a shallow failure mechanism in the long term, which you can see in those top right-hand diagrams, because they range from 25 years or less than 25 years up to around 80 or 90 years. Just to add this, while we're looking at these curves, within Achilles, we are looking at implications for slope management. So this isn't in the paper, but we've started to look at the role of interventions and the timing of interventions in reducing the deterioration of slopes. So this is an example of adding soil nails to a London clay slope that is 8 meters high. And in the diagram at the bottom, you can see curves showing reduction in factor of safety over time within the simulation. And shown in green, amber, and red are the intervention, which is the soil nails being added at different points in time. So green is when you've added the soil nails after 25% deterioration of factor of safety, and so on. And what this is showing is that early interventions to stabilize the slope when it started to deteriorate can actually lead to quite significant increases in the serviceable life of that slope. Okay, so just to conclude something, bring some conclusions from the results that I've presented. What I showed was a hydromechanical model, coupled hydromechanical model that was verified against field monitoring data and then used to forecast the longer term behavior of 120 years. What we can conclude is that the initial response of the cut slope to the excavation process causes an increase in pore water pressure and swelling and outward movement of the slope. And during this time, the slope is most susceptible to deep-seated failure. And this is a quite well-known result, and it depends. Here we looked at a London case, the Newbury slope, but it will vary depending on the site-specific geometry, climate, and material properties. What we saw in this particular model is that in the longer term, so 15 years or more, the seasonal pore water pressures drive a seasonal ratcheting of the slope. And this causes strain softening that begins at the mid-slope and later progresses to the toe of the slope. Over decades, this becomes more and more prominent, and it actually alters the dominant failure mechanism from a deep-seated to a shallow failure mechanism. And it's important to mention here that this softened reduction in shear strength is permanent. So it's not only a response to changes in effective stress, it's due to the softening and strength reduction of that material. Therefore, this helps to explain why weather events on the national rail or highway networks can trigger failure in slopes that were previously stable under similar weather conditions. So they might be experiencing the same weather as they've had in the past, but actually the material strength has deteriorated due to these longer term cycles. Okay, So thank you for listening. I've talked about one particular case study here, but Achilles is a large project with all these universities here on the right. And I really encourage you to go to the webpage, achillesgrant.org.uk, because it outlines the project. And as you can see on the right hand of the webpage there, which is in the blue box, there's sort of short articles on each of the key papers that are driving the project, from the conceptual model to the performance curves to some of the simulations and some of the field work. And finally, I'd like to thank our supporters. So we have a number of industrial stakeholders who are listed along the bottom there, who really help steer the direction of the work, provide information, and help us to provide outputs that can be useful for industry. So thank you for listening, and I invite any questions.
Okay, thank you very much, Kevin. If anyone has any questions, if they wouldn't mind posting them in the chat, please, I will ask the speakers them.
Hi, can I just add one statement? Hello.
Sorry, how do we get the chat thing to pop up?
It's the speech bubble in the top right-hand corner.
Oh, thanks.
Hi, can I add one statement, if that's okay?
Yeah, go for it.
I'm aware of a project called Smarty, a European project happening at the moment as well. It's probably towards the end, between the University of Palermo, University of Nottingham, and I guess some collaboration with SNCF as well. They're literally focusing on the same sort of area as well. I just want to check that if you're aware of that, or has it been any sort of collaboration or comparison of the result, because they were doing the same sort of things.
Hello. I'll answer this. I should add that Fleur Loveridge is also here to answer any questions. Sorry, Fleur, I hadn't mentioned that just yet. I'm not aware of that project, no, and I don't think we're linked to them at the moment. But I'd be interested to look at that. I guess we are very focused on our assets in the UK and very focused on these high to medium plasticity clays and the particularly old slopes, which would be many of our network rail slopes. But yeah, if they have some similar age slopes, then I think that's something that, thank you for suggesting it, yeah.
Okay, Sean Tarrant asks, the consequences of wet periods, has this been validated by real events?
It's hard to use. So this I think if I understand the question correctly, these simulations, one thing is Newbury cutting hasn't failed yet. Well, it hasn't failed, so we can't validate that failure against that. And when we compare it to the national failures, for example, it's hard to use these models to predict the failure of an exact slope, because actually it depends on all those other conditions that I mentioned in the inputs to the model. So you'd need to make sure you have the correct geometry, the correct material properties, and the correct weather data for that site, I guess. So we're not predicting exact failures. In this, what this model is demonstrating is the mechanism of the failure and how that develops over long periods of time, and how it can make the slope a bit more susceptible to a failure when it's deteriorated. Having said that, there are other measures we can use to look at failures. So for example, you mentioned wet periods and real events. Yes, there's been, I think it was 2004 was a paper published using London Underground data, where they looked at porter pressures in the extremely wet winter of 2000 to 2001, where porter pressures were where the weather had been the most extreme weather event for a long time. I think it was a 1 in 200 year event, so that was like a extreme wet winter. And what they saw is London Underground went out and measured the water pressures across a number of slopes during that period and saw that they were very high. And if you use the SMD model, the soil moisture deficit model, and compared that to those failures, you would have seen that SMD was 0. Similarly, if you plot SMD soil moisture deficit, or I think some infrastructure owners use soil moisture index perhaps, they can also be related to wet winter weather. Well, they're driven by wet winter weather, but I think they've also been linked to real failures as well, if that answers the question.
Okay, thank you. Mike Barlow says, thank you for a very interesting talk. How widely has this been adopted across Network Rail for their asset management plans?
This paper was published this year, so I don't think it's been incorporated as yet, as I know, but Network Rail is one of our industrial stakeholders. So we're looking at ways to let this work input into what they're doing. And also we have a package within the Achilles Programme looking at design and decisions. So actually specifically looking at how we can translate outputs such as this model, but also the field work and the lab work into tools or design charts that actually might be useful for designers or for asset owners as well.
Do you want me to say anything more about that,
thank
Kevin?
you. Fiona.
Yes, if you had anything to add, yeah.
Yeah, I'll just add that the sorts of things we are working on in that package that that Kevin mentions are how we might translate the learning from some of the very time-consuming numerical simulation into more routine limit equilibrium analysis. Also thinking about how we might be able to make recommendations about how we assess the condition of these slopes, so how we work out where they are on these deterioration curves that he's been presenting, and that will help us, you know, work out the economics, whether we should intervene now or later to get the most cost and value effective remediation. So there'll be work forthcoming on these elements soon.
Yeah, thanks, Fleur.
Okay, thanks, Fleur. Fiona Thompson asks, can we apply analysis backwards in time, e.g. to clay cuttings already 120 years old?
Thank you, Fiona. Yeah, this links to what Fleur was mentioning. Actually, we're within what we're trying to develop in Achilles is these deterioration curves based on behaviors that we can simulate or that we've measured. And there is a package within the program for rapid asset condition assessment. So we have a team who are looking at tools, monitoring tools, or in situ investigations that can be undertaken rapidly to find out where a slope might be on that curve. So we might be able to say whether the clay cuttings have deteriorated and they're on the downward part of that upturn bath model, or if the measurements are showing that actually they're still within their reliable stage and they haven't deteriorated yet.
Okay, thank you. Mike Brain asks, as a slope experiences repeated seasonal movement, is there a point where it fails catastrophically, and can this be predicted in time or cycles?
Well, I think that's what this model is showing. So this is just showing repeated seasonal movement, and it's looking at how the if it were to continue in this particular slope for very long periods of time, then it fails when the factor of safety will drop below 1. What hasn't been shown in that model, the reason being is because the question was about this strain softening and how it's deteriorating the strength of the slope. If we translate that to a real slope, we obviously have extreme events. So the inputs to this model in that synthetic weather data are actually just average weather data. So our model is showing that that could lead to failure in this high plasticity slope, but it could happen much earlier if there's an extreme event that is enough to push the water pressures with that degree of material deterioration. That combination could cause a factor of safety of less than 1. The other thing to say about the full scale, about real slopes, is this is obviously one type of slope, so it's a clay, high plasticity clay slope, and it's on a London, it's just London clay foundation as well. There is obviously work needed to translate this to real assets, in that not all slopes are high plasticity clay. They might be medium plasticity clay, for example, and that is something we're exploring within Achilles. And you might also have different hydrogeological conditions at the site. So, for example, there's been work again on London underground assets showing that if your earthwork is underdrained by a more permeable layer, like a chalk or a terrace gravel or something, again, this might not be so much of a problem, and that slope might not fail either. Finally, this links to Fiona's question just below. The vegetation will affect the slope as well, and that's not something explicitly considered in this simulation, but it is something that we're considering within the Achilles program as a whole.
Okay, thank you. Fiona's got another question. Can you vary vegetation coverage in the analysis?
Yes, so that's something we're considering at the moment in Achilles. We can do it within the simulation. The challenge is making sure it's representative of what's really out there. So the very simple analyses that we've done within Achilles and within previous projects is comparing a simple condition of a grass-covered slope, which is what the Newbury slope was, versus an idealized tree-covered slope, where the vegetation, the trees can withdraw water from greater depth and cause much greater suctions, etc. But that's a very much work in progress, because it's quite challenging to validate that model, those sorts of models, against real field data.
Okay. Maru Ganada has a question. Network rail has earthworks that are generally older, so presumably the main risk is shallow failure. Are there any other solutions than the adoption of soil nails to extend the asset life?
Thank you. Again, Fleur might have input on this as well, but the modelers have started, when considering what solutions or remediation measures to include, we've been consulting with the stakeholders to the project, which you can see along the bottom of the slide, the main slide. And one of those solutions is soil nails. Another solution is regrading the slope, is something we're considering. Another solution, I believe, is putting retaining structure in there somewhere. And the fourth one, which is quite difficult to simulate, is the implications of drainage. So improving the drainage or changing the drainage on the slope. So again, these are things we can bring into the simulations, but it's taking time, because we need to make sure they're validated against real behaviors that we see in the field on our monitoring sites or on the sites that are monitored or owned by the asset owners.
Okay, thank you. Finally, Mohammed has a question. So, were there any consideration to use the DEM instead of the FEM to give a better accuracy in terms of forecasting the behaviour or the deterioration of soil?
Thank you. As far as I know, I don't think within the program we've been looking at DEM. It's been mainly FEM or finite difference, because there's actually, in terms of accuracy, to make something accurate, we need to, again, whatever we're simulating, we need to compare to things that we've measured, either in the lab if we're looking at material behavior, or in situ, and things that we can validate in the field against the monitoring data. So in terms of coupling that hydromechanical behavior, we've mainly been pursuing the FLAC simulations so far.
As far as I'm aware, there isn't a lot of experience of using DEM for that kind of problem. I think one other thing worth mentioning is that Achilles is also doing work to develop a new constitutive model for these types of materials based on the laboratory testing in the project. Now that's still underway, so it's not included in the simulations that Kevin has presented, but the intention is to be able to come out of the project with an improved option for simulating these types of behaviours.
Okay, thank you, Fleur. Has anyone else got any other questions? And yes, apologies, that was my cat. Okay, I'd now like to call upon Fiona Thompson to give a vote of thanks.
Hello, am I back? I think so. Anyway, Tom, I don't think you need to apologise for your cat. He was obviously showing approval for the talk. But I want to say perhaps slightly more relevantly, I think I can speak for the rest of London section and everybody and any of our guests who are here today, that I think we all very much enjoyed the presentation. I mean, I personally I have a slight bias towards geotechnical talks, I have to admit. So I've been quite spoilt today. I also have a lot of clay cuttings to think about. So again, for me, the research that Kevin and Fleur and the rest of Achilles are doing is absolutely spot on. And it's just for me, it's just amazing to see the possibilities and of where all of this could go. I mean, looking at the talk, first of all, the first thing we learned probably apart from Kevin's introduction was that Achilles is I don't know if we can actually count it as an acronym or not, but it's very clever. So, and of course, this leads on to what's the Achilles heel of our infrastructure, which I expect is a tagline that's also used on the website. And the Achilles heel is often Earth structures because they're seen as immovable objects that don't really do anything until they do. So, and I was very impressed to hear about the range of people involved. I definitely need some help with statisticians. I think as engineers definitely need help with money and time and just I suppose what we used to call big data, just the amount of results that we've got, and be able to get more results through the simulation techniques is also quite staggering, because we're used to having just our data, but now it can be combined with those of other asset owners and extrapolated, then so much the better. I was particularly excited to hear about synthetic weather data. I'd be very keen to know how that progresses in the future as well, especially because I know they will actually have to end up incorporating climate change or change it, yeah. And just also, I said, can we also apply it backwards? So can we determine what the weather was likely to have been over 100 years, and so therefore what's happened to our assets now? So that's something that's quite close to my heart. And also, I suppose I can't help thinking there's going to be lots more to come from this, which would be great. The areas I want to see more on, or in the future, and I'm sure Kevin and Fleur do as well, is embankments, for instance. Now, selfishly speaking, again, London Underground embankments are really awful. Compared to the Bionics, the Bionics fake embankment, because if I'm teaching everybody to suck eggs here, but in terms of the material for the cuttings, at least, we're going to be very similar between highways and railways. But when the embankment construction, because the railways tend to be older, or the older railways anyway, have a much more variable composition, and it'd be interesting to see how that gets modelled. But these are all subjects for future presentations, I expect. And I just want to say thank you very much to both Kevin and Fleur for joining us today. And now, if everyone can sort of somehow approximate a round of applause, that would be great. So obviously, that would sound a lot more impressive if we were all actually in the same room with you.